So I want to show you a neat application of the Serre spectral sequence that maybe isn't so computationally heavy as computing the cohomology of Eilenberg-MacLane spaces. We'll get back to those heavy-duty computations, but for a little bit of a breather, let's look at this application. And let me just remind you that the Euler characteristic of a space can be computed using homology. You just take minus 1 to the k times the rank of your kth homology group, and then add those all up. Okay, so the theorem is that if we have some fibration, so let's let this be a fibration, and I'm still trying to avoid local coefficients, so let's assume that pi1 at b acts trivially. On the homology of the fiber. And let's work with coefficients in a field. So for k, a field. Now let's also suppose that b and f are fairly nice, so I just want these to be finite CW complexes. So that their Euler characteristics are defined. Just trying to avoid any infinite sums here. Well, the claim is that then the Euler characteristic of the total space is also defined, and in fact, it's just the product of the Euler characteristics of the base and the fiber. Okay, so why should you believe that this would be true? Well, if our fibration is just trivial, meaning that the total space is B cross F, and the map down is just projection, well then the homology of our total space in field coefficients by the Kuhn theorem is just going to be the tensor product of the homologies. So the homology of B tensored over K with the homology of F. And you can use that to show that the Euler characteristic of the total space is just the product of these Euler characteristics. In fact, anytime you have such a decomposition. So really, our theorem extends this result to non-trivial fibrations. Okay, so let's go ahead and prove it. We haven't done a lot of proofs yet in this class. So much of it has been building up the machinery, so let's actually see a proof. Well, we'll use the Serre spectral sequence, and we want to do it for homology. So this looks like the homology of the base tensor the homology of the fiber. This is because we're working in field coefficients, right? So our E2 page splits up nicely as this tensor product, and this should converge to the homology of our total space in that field coefficients. And each of these pieces in the tensor product is finite, right? Because we're, well, what do I mean? I mean finitely many non-zero terms, because these were finite complexes. And so the spectral sequence collapses. It's a first quadrant spectral sequence with only finitely many non-zero terms. And so at some stage, we look at EPQ R naught, and that just is our E infinity page. So that's our kind of best sort of convergence situation. and we can just take this R naught to be large. Okay, so I want to use that to get at the Euler characteristic. Well, first I'm going to define ENR, a singly graded thing, just by taking the direct sum of a bunch of pieces. So on the rth page, I want to take all the p comma n minus p pieces. So this just means add up all the stuff that has total degree n. And let's do this for each r greater than or equal to 2. So I'm not assuming that we're at the infinity page, but also let's do this on the infinity page. Okay, well, really that's just the R naught page and R naught plus 1 and so on. Those are all the same. All right, well, then the point of this is that we now have ER star. This is singly graded. And it's a chain complex using the differential from the spectral sequence on the rth page. I guess we're doing homology, so this should be upper R. Okay, and when we take homology of that singly graded chain complex, well, that's precisely taking homology with respect to our dr. That's how we get the R plus first page. Okay, so we're off to a good start. We've got the Serre spectral sequence has a nice E2 page, and we've come up with a singly graded chain complex. And now the key is just to notice that the Euler characteristic of this singly graded thing on the E2 page, well, the E2 page is just the tensor product of the homology of the base and the homology of the fiber. So this is the tensor product, the product of the Euler characteristics. Okay, and also this, the Euler characteristic of this chain complex that we've made from the R page is the same as the Euler characteristic on the R plus 1 page. If you think about it, and whenever we have a non-zero differential, then we're going to have something in, say, degree n, kill something in degree n plus 1. These are just copies of the field, right? So they'll annihilate each other, no weird extension problems. And then our Euler characteristic is preserved because we took something from degree n and also from degree n plus 1. So actually, I guess that tells me that the Euler characteristic of the E2 page is the same as the Euler characteristic of the R page, is the same as the Euler characteristic of the R plus 1 page. Okay, I'm lying a little bit when I say page because I really mean collapsed into a singly graded thing. But that's going to stay constant until we get to the Euler characteristic for R naught, and that's precisely what we're calling our E infinity page. Again, collapsed into a singly graded thing. Well, in general, just knowing what's happening on the E infinity page is not enough to tell you about what's happening for the total space, right? Because it's just an associated graded for some filtration. But the key to finishing the proof here is that K is a field. So there's no extension problems. And so we learn immediately that the Euler characteristic on the E infinity page, well, it's exactly the Euler characteristic of the homology of E in those field coefficients, and that's the same as the Euler characteristic of the space. And so that completes the proof. We now have the product of the Euler characteristics is the Euler of the base and the fiber is the Euler characteristic of E. Okay, so I just thought that was a nice little application that was not so computationally intensive, give us a little bit of a break from those in-depth computations. But anyway, there are lots of neat little arguments like this, and so I'm hoping to show you a few more fun applications of things that you can learn from the fact of having a spectral sequence without even doing really any hard computations. But again, this generalizes this fact about the product of Euler characteristics to any fibration. Locally trivial is enough. All right, let me stop there.